in this part 3 of solving example 12.4, we have calculated almost every single member force. In fact, we have all but one. All right, we've gone through and we're over here at the left side, then the right side, then we started feeding our way along and up and kind of zigzag our way around, gotten here, and we're almost done. I've now transferred over what we did in steps 7 and 8 to get member CH. That was one of the ones we wanted. CG, that was also one of the ones we wanted, right? And as we get done, get ready to do GH, we're going to find a way to double check our work. A lot of math could have done easily made a lot of mistakes, right? So we're going to go up to joint H, where right now we know that we have the diagonal chord member that puts the joint into compression at 200.1. We have the vertical attached to that joint that pulls on the joint at 100, and then we just discovered that the member CH is in compression at 80. Correctly here, right? So we'll do summation of forces upwards as positive, and so we'll have 200.1, which is really 200.0976, and then to get the vertical component, we'll have 4 over root 41, right, minus the 100, and then plus 80 times 4 root 41, and then minus GH 4 over root 41. Everything was at a common angle here, and that's all equal to 0. Okay? So maybe to make this math a little bit easier, it might behoove us to just multiply all the way through by root 41 over 4, and take that times 100. Right? So that becomes 160. Right? We had then put a minus there, plus 200.1 plus 80. Okay, so that's 120.02. How about that? That's a very interesting number running around there, right? It's got to be taken to the other side, or does it? Oh, the GH can go to the other side. So it means that we actually, when you solve this equation all the way throughout, GH is equal to a plus 120.02 ish, right? And so, and that plus means we assume the right direction. That means it's in compression, right? We can check our work here by sum of forces in the X. So let's do that. We've got 200.1 times 5 over the square root of 41. Of course, 100 doesn't come into play. We get minus 80 times 4 over root, 5 over root 41 for the horizontal. Remember, that's a 4, 5 square root of 41 triangle, where 4 is on the vertical. And then minus the GH that we just found is 120. Ooh, I like this. 5 over root 41. And we hope that equals 0. We could get rid of the factor out 5 over root 41. We got 200.1 minus 80 minus 120. Within a rounding error, remember that 200 wasn't really 200.1. It was changed real close, but we got a little bit of rounding in there, and that's going to be equal to 0. Good enough, right? And we could say let's stop there because that all sort of worked out, but let's not. Let's actually feed this all the way through and see what happens. Now, if we go to the crown of the truss at G, we found out that we had 150 kips of tension in that vertical member CG. We found also 120.1 kips in GF or FG. Right, that's compression. And note that the angles of those two diagonals are the same, so it really shows out by arguments of symmetry that GH had better be 120.1, and indeed that's what we found out in the previous one. Well, again, there's a rounding error there, presumably between 120.02 and the 120.0976 that we had found. That's darn close enough. That's out in the fourth digit of a difference. So that all works out well. Now note, we could have skipped step 9 to step 10 to find what GH was and then checked it at H as well. A lot of different ways you could do that. And ultimately how I would represent this, if you go back to our little summary sheet, you could do the free body diagrams just like we've got shown here. That's one way to have done it. For perfection's sense, I'm going to call that 120.1. Right, we could do it that way. That's not the way most people do it because that's just too much effort to draw all those little free body diagrams of the joints. And remember, I only did that as a strategy thing, but that I usually don't do it. I can do it by eyeball of going through here and then start doing all the work. So what I do as a final answer here is I'm going to come along to the member AH. It had a member for 200.1 kips, and it was in compression. So note how I'm writing these. I'm putting the member force on one side, whether it's compression or tension on the other side. Some people will put that right next to each other and get rid of the kips entirely and just write a note to the side that says all forces and kips. The bottom chord was 156.25 kips in tension for AB, getting carried right on across to BC. As we cross over that middle joint, that became 93.75 kips in tension. We had 0 force members, right? We had the vertical BH and 100 kips in tension. CH is 80.0 kips in compression. And let's see, this far diagonal was 120.1 kips in compression, right all the way up. And then finally that vertical was 150 kips in tension. Very interesting. So note here that we have these 0 force members. A lot of people always ask, well, then what's it doing in the structure if it doesn't have any force? Well, you know, we've ignored the self-weight of all the members, so there's a little bit of force from that. And understand our load pattern won't always be what's shown here. If this is in a bridge, you really understand that. But even in our analysis of, say, building trusses, you look at a variety of different load combinations or load cases, and this is just one that represents where we do have some 0 force members. That's one reason why you have them, is that you might have other load patterns.